All right, let's go over the test that we just had. 6 cosine x. Cosine goes this way, and it has an amplitude of 6. And if I put 4 in there, I get cosine of pi over 2, which is 0. So at 4, it hits 0. And at negative 4, it hits 0. So it's going to be a cosine curve. Comes up, goes through 6. It comes down through 4. And then it'll go back up. We'll clear down to negative 6 here at negative 8. And at positive 8, it'll be down to 6. That's the cosine curve. And this is a parabola that's down 16, 10, 11, 12, 13, 14, 15, 16. And since it's x squared, if you move over 4 squared is 16, so it hit there. So it's a parabola that's in here that hits at 4 and minus 4. So we want the area between these two. And so the top curve is this one. So it's going to be the integral from minus 4 to 4 of f of x minus g of x. This one minus this one. So to type that in on my calculator, I'd go to the y equals, type in 6 cosine pi x divided by 8 in y1. In y2, I'm going to do x squared minus 16. And I'm going to quit, and I'm going to go math integral from negative 4 to 4 of vars, y variables, y1 minus vars, variables, functions, y2, dx, enter, and the area is 115.89-ish. That's number 1. Number 2. It's 2 divided by the square root of 1 plus x squared. Zoom 4. So it goes through 2 and it tapers off. And we're supposed to do from 0 to 3. This rotate around the x-axis, so it would do something down here. Probably easiest to do a disk, vertical slice here that spun around. So it'd be the integral from 0 to 3 of f of x squared dx pi r squared times the thickness. And so if I wanted to write it out, it'd be pi 0 to 3 of 2 over square root of 1 plus x squared dx. Calculator, it'd be math 9 from 0 to 3 of pi squared dx. And I get 15.695, 15.70, approximately 15.7. Okay, number 3. Got to graph it. X squared, 0.01124. And over here, that's a rough sketch of this, where this is 4 and 2. X equal 2 would be here. So I get this region. Now, filling that in might cause it harder to see where I put slices and things, so I'm going to erase that. But that's the area that we want to look at. I probably should have doubled the size to make it a little bigger to see. Make this 4 and whatever. Between the x-axis, 2, and the curve. So that's this area. And I'm going to spin it around y equal -1. So this is 1 above, so it'll go to 1 below, -1. This is 1 above, so it'll go 1 below. This is 5 above, and so it'll go 5 below. 1, 2, 3, 5. So this area will come up. There'll be a gap in here, up, and go down through this area. Okay. So now I'm going to make let's see, we need to do this with a disc washer. Well, this is the axis, and if I'm doing disc washer, I need to do a slice perpendicular to the axis, which means I'm going to get a slice down here. This is going to come out and go into there. This is the inside. There's a hole in this. Kind of trying to draw it lightly here so we can do the other. But hopefully you can see a washer there. And the volume, or how to find the volume of a washer, it's pi r squared h. For a disc, it's a short cylinder, pi r squared h. But there's a hole, so we have to do minus pi r squared h. And on that, the h, the height of these cylinders, if I draw this thing laying down on its side, it's a washer. It's a cylinder, a very short cylinder. The shortness is in this direction on the graph. It's dx, that's the height. And the hole will have the same height. And there'll be a large radius and there'll be a small radius. So it's going to be, there's a pi in both, so I can pull that out. The large radius from the center to the curve, that's up there. Well, if I'm hitting the curve there, that's a point on the curve, and so a point on the curve, as we've talked about in class, has coordinates x, y, where this is the x, how far to the right, y is how far up. So if this is y, that's not quite the radius. The radius goes from here to there. So it's y and one more. And I don't care that this goes down or up or whatever. It's y plus one more. So the radius for the large disk is y plus 1. and the h is dx, and we got the pi. And for the whole, I got another color here. Yeah, looks like I happen to have a lot of blue pens. Thought I had a red. Somewhere I have a red. I don't see it. Okay, well, we'll just continue with what I got here. I'll do pencil. The whole is determined by this line and the x-axis, which are always 1 apart. So the radius for the whole stays 1 the whole time. So this is 1. And we got to square it. And this is also a dx. So I'll just move this dx out here for the whole thing. And I want to integrate this. The x is going to start here and work all the way over here. We're going to do these little discs all the way out to the outside. 0 to 2. That's the setup for the disk method on this. Now the shell method, just so that you can see it, I'm going to redraw this here for those of you who have a hard time seeing this. So we had a parabola that goes like this, and the x equal 2. This was 4, and it got spun around y equal minus 1, which means it's going to be down here. And it's spun around. So this is coming clear down to here and going back. There's a hole in this thing. And this is spun around. So if you were to turn it, it could be something that maybe a flagpole stuck into the hole and it was a base for holding it, or a Christmas tree stand or something. Okay, but that's kind of what it looks like. And we're trying to just find the volume of this, not the hole. Now, if I take and slice it again, but this time, since I'm doing the shell or ring, I have to slice it parallel to the axis. And if I follow that slice around, it'll be down here. And it'll come around like this. And I've been calling this a piece of pipe. Maybe you want to think of it as a band, like a wristband or a bracelet, or I don't know, something, a band that you tie around something, but it's empty. If I lay it on its side, it looks like a piece of pipe to me. But anyway, it's got a thickness to it. And we're making this have very little thickness. And it looks like that. Do you see how that band stands up, fits in this? And there's other bands in here. There's bands that are taller, but smaller radius. And these bands can fill up this object also. So when we're doing bands, the distance around is one dimension, the height of the band, and the thickness of the band. If you lay that band out, it makes a long, thin rectangular box. So it's going to be length times width times height. So the length is 2 pi r. I'll just call that the height, even though it's going sideways here. And the thickness, I'll call T, or for thickness. And I got to add that up. Well, the 2 pi can come out. The radius is going to be again from the axis out to where I made that. And this, where it hits the curve, again, this is still y, and this is still x. And so the radius is y plus another unit. I don't care whether it looks positive or negative. It's y plus one more unit. So the radius is y plus 1. This height is from here to here. Now x is from here to here, so it's not x. This whole length was 2, because it was at x equal 2. All of this is 2. We want just this, which is the 2 minus the x. It's x less than 2. So it's 2 minus x is the length of that bar. And then I have to do the thickness of this band. The thickness, that's the thickness of my mark, which is up and down. It's a dy thickness. And y would have to go from 0, the first band that we're going to get, all the way to the little, very short and very big around band out here at 4. So it's going to go from 0 to 4. Now, that's kind of the rough setup for the two methods. Now there's some things I need to take care of. In this one, it's dx, and I have a y. Well, up here, y is x squared. So I just put an x squared in here, and I'll have the integral I need for this. So this one will be, I'm going to put it down here so I can show you the work on this. So this is going to be x squared plus 1 squared pi integral 0 to 2 x squared plus 1 squared minus 1 squared dx. So this is for part B. And for part C, it's 2 pi integral 0 to 4. Now I have to have it in y's. That's a y, so that's okay. And it's 2 minus x, so the x has to go. X is equal to the square root of y. So 2 minus square root of y dy. Now I only need to work one of these out, but I'm going to work them both out here, hopefully without too many errors. So if I got x squared plus 1 and I got to square it, I got to take x squared plus 1 times x squared plus 1. That's x to the 4th plus x squared plus x plus 2x squareds plus 1 and minus 1 are going to cancel. And now I have something I can integrate. So it's pi x to the 5th over 5. And this will be plus 2x to the 3rd over 3. Evaluated from 0 to 2, which is going to be pi 2 to the 5th is 32 fifths. 2 to the 3rd is 8 times 2 is 16 plus 16 thirds. Put in zeros, I get minus nothing, and also times pi, but that's going to disappear, so there's an answer. Now let's do this one. So these need to be multiplied, so I'm going to get 2 pi integral 0 to 4. Y times 2 is 2y. Y times the square root of y, that's y to the 1 times y to the half. So that's, it's minus y to the 3 halves, 1 and 1/2. 1 times 2 is 2. And 1 times the negative square root of y is negative y to the 1/2 dy. All right. None of these are like terms, so I can't combine them. So I just got to integrate each one of these. So 2 pi and 2y integrated is y squared. Antiderivative of this, or integrated, that would go to 5 halves. Y to the 5 halves divided by 5 halves, which is times 2/5. Integration, the antiderivative of 2, since the variable is y, is 2y. Antiderivative of this is minus, it'll go from 1/2 to 3 halves. Divided by 3 halves, or times 2/3. Evaluated from 0 to 4. Definitely the more messy one here, but we got to put 4 in, and then we got to put 0. We can see that there's a y in all these, so putting in 0 is going to cancel everything. So I'm just going to have the 4. I'm going to have 2 pi. 4 squared is 16. The square root of 4 is 2. To the 5th is 32. Times 2 is 64. Put 4 in here and I get plus 8. Put 4 in here and take the square root. That's 2 to the 3rd, which is 8. Times 2 is 16. So 16 minus or plus 8 is 32. 5 into 64 is minus, 5 into 60 is 12. So this is minus 12 and 4/5. And then 3 into 15 is 5 and 1/3. 5 and 1/3. Now I could just type these in my calculator and check if they match, but let's do some math here and do it this way. So 32 minus 12 is 20, minus 5 is 15, and then I'd have minus 4/5 and minus 1/3. And that would be times 2 and pi. So the common denominator is 15. So 15 times, how did I get 32? 16 plus 8 is not 32. Don't do that. 24. And that is plus, isn't it? Yeah, 2y, yeah. 24. How did I get 15? Oh, 24 minus 12 is 12. Minus 5 is 7. 24 minus 12 is 12. Minus 5 is 7. There we go. This is better. Common denominator is 15ths. So this one would be 12 15ths. And this would be 5 15ths. So that's minus 7 15ths. Minus 17 15ths, or minus 1 and 2 15ths. If I take 1 off of this, I get 6. And then if I take another 2 15ths off, I get 5 and 13 15ths. That I got to take times 2 and pi. So I got 10 and 26 15ths pi. And 15 goes in there once with 11 left over. So I get 11 and 11 15ths pi. Now let's check here. So common denominator is 15. So if I take this times 3 and 5, so that's 96 15ths plus 16 times 5 is 80 15ths, which is, yeah, I would have been happy with this answer or this answer, but these I'm just trying to show that they're the same. That's 176 15ths. 11 times 15 is 165, plus another 11 is 176 15ths. That's what this is. That's what that is. All right, that took way too long to do all this. I would have been happy there or there, and you only had to do one of these. This one turned out to be the easier one. Okay, on to the next problem. Determine the work done pumping water out of a full isosceles trapezoid water trough. So here's the water trough. It's completely full. 4 foot wide here, 6 foot wide here. And we're pumping it into a truck that's up here, another 7 feet higher. Okay, so we got this water that's in here. So this is my slice of water. It's basically a rectangle. And I've got all these slices of water in here. And I'm lifting every slice up to the truck. So, since this is in feet, we're going to use the 62 per cubic foot. So the weight of this slice is the density, which is pounds per volume. This is a weight density, 62.4 pounds per cubic foot. So to get the weight, the force, weight is a force. To get the weight, I have to multiply it by the volume of what I'm lifting. And I'm lifting this slice. So I need a coordinate system on here. So I'm just going to put where this line is, where that is. This is where most of you would write it. And so if that's the case, and this is on a side here, it's going to have coordinates x, y, where this is x and this is the y. So my slice is this length doubled, so it's 2x. This length, which is 8 feet, and the height of that box, because it's length times width times height. The height is in the y direction, dy. So there's the volume that I'm taking times the weight density. So that turns out to be just a weight, and work is force or weight times the distance I have to move. And I'm moving this slice from here to the top of the truck. But it's going to change as I do different slices, so I can't just say it's 7.5 feet or something. But I know this is y, and from here to there's 2 feet, and 7 feet from here to there's 9 feet. That's 9 feet, but this slice is up y, so it's 9 minus this y. I'm only lifting it 9 minus y feet, not the whole 9, just from where it's at up. And I have to do that for all the slices, so I'm going to add this up for all the slices which appear to be between 0 in the y and 2 in the y. And this is pretty much good to go, except for this is dy, that's y, that's cool, but that x needs to go. Now you can do it in ratios, but I've been decided just to stick with, let's find the equation of this line. Find the relationship between x and y. It's determined by the slope of this side. In fact, this point is, if this is 4, this is 2, so it's 2 in the x and not up and down any. And this point is, if that's 6, this is 3, so it's 3 in the x and up 2. And I want the line that goes through these points. So it's y equals, see the slope. 0 to 2, it rises 2 as it runs from 2 to 3, which is 1 times x. So it's y equal 2x plus something. And if I put 2 in, I'm supposed to get 0. If I put 2 in here, 2 times 2 is 4. So this would have to be minus 4. So here's the equation of this line, but I'm trying to replace the x, so I add the 4. And actually, I can just replace the 2x with y plus 4. Or I could divide by 2 and then put that in for x and then multiply by 2, and it would just be the same thing as putting for all of this y plus 4. So I have 62.4, 0 to 2 of, let's see, 8 times this is 8. Well, I could just pull the 8 out because it's times everything. So I got y plus 4 times y minus 9. 9 minus y, excuse me, I said that wrong. So this is 9y plus 36 minus 4y. Oh, let's put that together. 9y minus 4y is 5y. And minus y squared. Minus y squared plus 9y minus 4y plus 36. So the antiderivative of this, I mean, you don't have to. You can just type this in the calculator, but the antiderivative of this is negative y to the third over 3 plus 5y squared over 2 plus 36y evaluated from 0 to 2, and all that answer times 8 times 62.4. You can put 2 in for the y's, and zeros won't produce anything, so we're going to get negative 8 thirds. 2 squared is 4, divided by 2 is 2, times 5 is 10, plus 72 times 8 and 62.4. I'll work that out. Yeah, I know. Negative 8 divided by 3 plus 10 plus 72 times 8 times 62.4, and you get 39603, and this would be, we're taking the weight, which will be pounds, times the distance, feet, so this is foot pounds. Now, let's just go back here and do it way back here when we could have. Math 9, 0 to 2 of 62.4 parenthesis x plus 4 close parenthesis open parenthesis 9 minus x close parenthesis dx, and I am missing something. Oh, I missed the 8 in here, times 8. And there's the same answer that we had up there. This one, vertical tank with a height of 15 feet. So we're in the English system. It has dimensions of 8 feet and 6 feet. Now you could have put the 8 and 6 there, it doesn't matter. But they're the sides. Pressure at the bottom of the tank. And it's only filled to within 2 feet of the top. So the pressure is simply the weight density, 62.4 in the feet system, times the depth, and the depth of the water is 13 feet. And this is pounds per foot cubed. So we're going to get pounds per square foot. For this one, 62.4 times 13 feet deep, 811 pounds per foot squared. That's pressure. Now B, determine the force on the smaller side. So if I make that 8 and this 6, 6 is the shorter. They're both tall, but this is 6 by 15, but the water's only to 13. So to do B, the pressure changes as you go down. So when we got something changing, it kind of says we're going to have to add up using calculus. So we're going to figure out how much pressure is on this area. Remember, pressure is force on an area, and we want to know the force pushing on the side. So we've got to find the force, which is pressure times the area, on each of the slices on the side here. The slice is 6 feet across, and it's dy high if you decide to make y go vertically, and it doesn't matter where you put this for the coordinate system. Vertically would be y, the way you guys like to do it. So the height is dy, and this is, if you put it in the middle, it's 2x, but it never changes, so it's always just 6. So it's the integral of the pressure at this depth, which is 62.4 times the depth. That's this. If you put your coordinate system here, then this is y, up to y, and this whole thing is 13, so the depth of the water is 13 minus y, 13 minus the y. That's the depth. So there's the pressure that's pushing on 6 wide dy height area. This is the area that this pressure is working on. And we're going to have to do that for y going from 0 to 13. So that would be, it can take the 6 and the 62.4 out. 13 would be 13y, and the antiderivative of y would be y squared over 2, evaluated from 0 to 13, times 6 and 62.4. You put the 3 in here and you get an answer, but you could also just type this into the calculator, which is math 9 0 13 62.4 parentheses 13 minus x and 6 and x, and you get 311.50. And this is, we're looking for a force. The force is the pounds, the number of pounds of force pushing on that end. All right. 6. This is an improper integral. So we need to do the limit, because it goes to infinity, of b approaching infinity of the integral from 2 to b of 2 over x ln x cubed dx. Now to do this, I gave you a hint. You let u equal ln x. Its derivative is going to produce an x, a 1 over x, which will end up in the numerator and cancel that x. So dx, we're going to replace the dx with x du, multiplying both sides by x. So I have the limit as b approaches infinity, integral from don't know to don't know, because I'm changing to a u variable. I could put in 2 here to be ln 2 to ln b if you wanted, but I'm just going to come back to x's. So this is going to be 2 over x u to the third. A lot of you left the 3 out. And the dx is equal to x du. And the x's cancel. The 2 comes out. And so we're just doing the limit as b approaches infinity of the antiderivative of the x's are gone, of the 2 pulls out, 1 over u to the third, which is u to the minus 3. And the antiderivative would be u to the minus 2 over minus 2. 2 times minus 2 u to the minus 2, which, no, over minus 2. U to the minus 2 over minus 2. Let's write it that way. And evaluated from I don't know to I don't know. Limit as b approaches infinity. The 2's cancel, the minus doesn't. And u is ln, and it's to the minus 2. So that means it goes into the denominator of ln of x to the 2 power, because it was to the minus 2, take it down, it's to the plus 2 power, evaluated from back now to x's, so we're going from 2 to b, and I got to plug those in before I take the limit, so I'm going to have the limit as b goes to infinity of minus 1 over ln of b whole thing squared, minus and minus plus this with 2 put in, and what happens with this? If you are in doubt, not sure what happens to that, graph it. What? Minus 1 divided by ln x whole thing squared and we want to know what happens when the x to the b gets really large. So I'm going to go zoom 6, and it looks like it's getting closer and closer to 0. We can look out there further, and it doesn't do anything except get closer and closer to 0. I can push trace, and it says it's negative 0.06, negative 0.05, negative 0.04, and it just keeps getting closer and closer. This is headed towards 0, and so this is gone. This will be a finite amount, so now we're actually taking the limit. When we're figuring out what this goes to and this goes, that's a constant. So the answer to this problem is 1 over ln2 quantity squared. And it converges. It's limited in size. Okay, finally, the last problem. Population density based on the distance from the center of the city is this. If I put in 0, it's saying there's 450 people per square meter. But we're supposed to do it as you go out further. This denominator is going to get bigger, and then the amount of people is going to taper off. It'll never go to 0, but it'll get closer and closer and closer to 0 as the denominator gets bigger. But we only need to go out 10,000 meters. So if I'm looking at the center of the city from the aerial, it's kind of real dense in the center, and then it gets less as we move out in all directions. This is how many people per square meter. So I got to go out here and count the people on a ring out here, and on the ring in here, and on a ring in here. I'm doing people on all these different rings and adding them up until I get to 10,000 meters from the center. That's 5 kilometers out. No, 10 kilometers out. Okay. So I'm integrating from 0 to 10,000 meters, 10 kilometers. Population density times, that's per square meter, times the area that population density is on. Well, that's a ring. It has a radius x. And it goes clear around, so it's 2 pi r. So it's 2 pi x is how long this ring is. And if I cut that band and open it up, it's 2 pi x going clear around, and its width is in the radius directions, dr or dx, and the area of this, where this population is on, is 2 pi x dx, and that's all there is to it. Now, to do this problem, you could do a u sub for that, and that you'll get 2x, and then it'll cancel the 2x, and this is pretty simple to do with u sub. But I can just also type it into our calculator. Yeah, I know. Math 9 0. I do that to 10,000 of 450 divided by parenthesis 1 plus x squared times 2 pi x dx. And there are 26,000 people within 10 kilometers of the center. 26,041. At least that's what the model predicts.